Right, hello everyone. I wanted to make a small little lesson on haloalkanes. So haloalkanes are any halogen that is attached to an alkane. So what is a halogen? Halogen is anything in group 17. This includes things like chlorine, chlorine, bromine, and iodine, and then that AT1 that is just trash. Right, alkanes. Alkanes are anything that involve the formula CnH2n plus 2. So that means if I've got a single carbon atom, and it's bonded to 4 other hydrogen atoms, I have got a alkane. If I have got, say, 2 carbons, then those 2 carbons will be bonded to 3 other hydrogens and will make an alkane. Alkanes are structures made up of carbon and hydrogen that involve only single bonds. So they're your simplest form of hydrocarbon. This thing right here is ethane, right? How do we name them? Well, we've got our list of meth, eth, prop, bute, pent, hex, het, and oct. These all stand for 1, 2, 3, 4, 5, 6, 7, and 8. And this is how many carbons are in that chain. So methane will have 1 carbon, ethane will have 2, propane 3, butane 4. You get the idea. These are all followed by the suffix of ane, A-N-E. This means that it is a alkane. It has got only single bonds, right? So there's none of this, double bond carbon malarkey or triple bond carbon malarkey, right? Or this absolutely impossible beast over here. Quadruple bonds for carbon don't exist, right? An ane or an alkane only contains carbon single bonded to carbon. Awesome. Glad we cleared that up. So a haloalkane is just an alkane with a halogen group attached to it. And a halogen group can be any of these over here, right? So a halogen can be fluorine, it can be redly drawn chlorine, bromine, or iodine, and we're not going to talk about this one because no one really cares. Right, moving on. Cool. So the basic structure for a haloalkane will be a carbon atom that is bonded to, say, a single halogen, and this carbon will be bonded to, say, more hydrogens, like so, and then we're just going to put an R or remainder group there. This remainder group basically means it's something else. It's some other group of carbons that just keep going and going and going. We don't care what it is. We're only interested in this group over here, right? So we're only really interested in this bond here. This bond in red is our haloalkane. This is the thing that we're interested in. Why are we interested in this? Well, we're interested in this because this particular bond is quite reactive, and it allows us to do some quite interesting things. As you already know, bromine has got a slightly higher electronegativity than carbon. Carbon's got an electronegativity of about 2. Bromine, I've forgotten the exact number, but it's a little bit higher than that. Therefore, this bond is going to be slightly polar. Because this bond is slightly polar, it means we now have a dipole in our molecule. This means that things that are particularly more positive, right, slightly positive things, are going to be attracted to our bromine, and things that are slightly negative are going to be attracted to, say, our carbon. What does that include? Well, that includes various things that have got electrons, right? So if we've got our ammonia molecule here, right, NH3, here we go. As you know, it is a trigonal pyramidal structure. So we've got a hydrogen stuck down the bottom at 109.5 degrees each, and we have this little lone pair sitting at the top. Now this lone pair is rather negative, right? Because you've got two electrons chilling out here by themselves. So this lone pair is going to be attracted to this carbon over here. This is kind of, how the mechanism of the reaction is going to function. Cool. So how does this all work? So we've got various reactions that we can carry out with our haloalkanes. The most general one will be, say, haloalkane plus a base, so just hydrogen, so, hydroxide, aqueous, right? This will produce, what is this going to produce? Let me clean this up a bit. This is going to produce an alcohol. And it will also produce hydrogen halide. Right. So what is that going to look like at the end of the day? Well, we've got a haloalkane, so that could be, I don't know, 1-chloroethane or something like that, reacting with a strong base in solution. This is done in the presence of water, right? So you can see the little aqueous symbol here. This means that it is dissolved in solution. This down goes to alcohol, so 1 alcohol plus a hydrogen halide. Something that I just figured out in post-production is this should not be a hydrogen halide, but should just be a halide. Apologies. How does this look like in terms of a chemical formula? Well, we can represent this as CH3 to CH2 with a, say, I don't know, we'll go for chlorine because it's easier with the chlorine. So this will be chloroethane, right? It's got a chlorine, it's on an ethane, chloroethane. We're going to be reacting this with a hydroxide molecule, right? It's negatively charged. Cool. What happens with this? Well, make a start. Well, because this little carbon here is going to be slightly positive, and this chlorine is slightly negative, we've got a negatively charged hydroxide ion is attracted to carbon there, right? So a hydroxide molecule attacks our slightly positive carbon molecule. What this does is it breaks this bond here, right? This bond breaks. This means that each one has now got a single valence electron. Sorry, a single non-paired electron. As that bond breaks, so 1 electron from the bond goes there, 1 electron from the bond goes there. This then reacts and forms a bond with that. The resulting overall structure is CH3, CH2, and we now have got a hydroxide group attached to that carbon. What then happens, let's fix that up. What then happens is we now have got a chlorine ion that just kind of gets ejected. It just gets rejected away from that molecule. Sweet. So that is what we call a substitution reaction. This is called a substitution reaction because we are substituting our halogen group here with our hydroxyl group here. Sweet. So we start off with this bond here. We break that bond. We then add our hydroxide to our carbon, and then the chlorine just travels off on its own merry way. Right? So this gives us this at the end of the day. We've got our alcohol. This molecule here is ethanol. Sweet. Next one. We have got our haloalkane. And we're now reacting our haloalkane with ammonia, right? Plus NH3 ammonia. So as you know, ammonia is this molecule here. we've got 1 nitrogen and 3 hydrogens and a lone pair of electrons sitting at the top. Right? So this will react here. Got a little smiley face for my little reaction forward symbol, and we make a thing called, right, give me a moment, an amine. Right? And then at the end of the day, we eject out our hydrogen halide. Sweet. So we'll do the same thing again with our alcohol. We'll start with chloroethane over here. So that'll be CH3 with CH2 Cl. So that there will be chloroethane, chlorine here, ethane over here. Sweet. We're reacting that with, say, ammonia, NH3. Sweet. What that does is that produces CH3, CH2, fix up that 2, and it forms an amine group. An amine group is NH2. So we go from ammonia, which is NH3, to an NH2. So in the process of forming this amine, our ammonia will lose a hydrogen and bond to our carbon here. So we now have got an amine over here and our ethane over here, right? So this molecule here is going to be ethane 1 amine, right? So ethane 1 amine. So the ethane denotes that it is an ethane or an ethyl over here, so 2 carbons. The 1 designates which particular carbon amine is going to be attached to, and amine designates that it is that this molecule has an amine group, right? So ethane 1 amine. You can also call this ethyl amine, basically denoting that we've got an amine group that is attached to an ethyl group. The amine group is this group here, so the NH2, and ethyl is this group over here, right? So you might be familiar with this name here, or something similar. After all, in Breaking Bad, they use something called, methyl amine, which is this structure here. Right? So methyl, because we've got a methyl group here and an amine over here. So methyl amine. Sweet. What we also produce in this reaction, yeah, is also our hydrogen halide. So this is ethane 1 amine plus HCl. Now the hydrogen halide will be pretty much, well, this halide here will pretty much be whatever it was what we were starting with over here. So if we're using, say, bromine, we'll have hydrogen bromide. If we had, say, fluorine, it would be hydrogen fluoride. You get the idea. In this case, since we're using chlorine, it is now hydrogen chloride. Awesome. So the overall reaction is an amine plus is a hydrogen haloalkane plus ammonia solution. In this case here, our ammonia solution is just going to be aqueous, and we're going to then react it to form an amine. An amine is just a NH2 group attached to any other carbon chain, plus a hydrogen halide. If you were to represent this as an equation, we've got CH3, CH2, Cl. So this is going to be chloroethane reacting with ammonia, also aqueous. Shit. And this forms ethane 1 amine, or CH3, CH2, NH2, plus our hydrogen halide. In this case, it's going to be hydrogen chloride. This is also something that we call a substitution reaction, because we are substituting our chlorine for an ammonia. right? So we're removing one group and switching it out for another, breaking one bond and forming another bond. The rest of the molecule has been unchanged. We're just changing one group or substituting one group out. The next one's going to be slightly different. Right, this is going to be an elimination reaction. So if we've got a haloalkane and we react it with a strong base again, so OH minus a hydroxide over there, but instead of doing this with an aqueous solution, so just water and all that, we're going to be dealing this with alcohol, right? So something like ethanol would be completely fine with this. So you'd pretty much do this in a strong alcohol solution. Cool. So what this forms is an alkene, right? An ene, not an ane, right? So the ene suffix here denotes that there is a carbon-to-carbon double bond somewhere in the molecule. None of this single bond malarkey. Cool. So we get an alkene, we produce water, H2O, plus rejected, which one are we using? I'll be using, say, chlorine again, our rejected halogen. In this case, it's now going to be chloride. So we start off with, say, halide. Sweet. So we start off with our haloalkane. We're reacting this with an So we start off with our haloalkane. We're reacting this with a strong base in an alcoholic solution. This creates an alkene plus water. The water here is going to be our hydroxide plus one of our hydrogens that we're ripping off our haloalkane. And we're also going to get our halide ion coming off. And this is going to be our fluorine, our chlorine, bromine, or our iodine, and whatever the hell this thing is, right? We are not talking about that one, right? So remember, we're producing an alkene in this reaction. It has got a carbon-to-carbon double bond. What does this look like in, say, chemical form? Well, we can have our CH3, whoops, 3 plus CH2, Cl, going for chlorine again because it's really, really easy. We're reacting that with our OH minus in an alcoholic solution. What this now produces is CH, no, 2 double bonded CH2. This is now our ethene or alkene plus H2O plus Cl minus. Right, so we're losing our chlorine or chloride. We're losing one hydrogen, which gets added to our hydroxide, and we are left with our alkene. Right, so this particular molecule here is ethene. Right, ene denotes that it's got a carbon-to-carbon double bond here. Right, and eth with 2 carbons. So in this case, our molecule is now going to be ethene, and it's going to be symmetric. Sweet. All right, so we call this type of reaction an elimination reaction. The reason why we call this an elimination reaction, I'll just fix this up quickly, is because we're eliminating a hydrogen and a chlorine from the molecule. We're removing them, we're kicking them out. Alright guys, I hope that was helpful in learning about how haloalkenes react and some of the various products that they can form. Have a good one.